Thank you. Thanks for the introduction. So, as he said, my name is Caicedo, Syracuse University. My background is in engineering, but I worked at the School of Information Studies. I had a Ph.D. in information science, so I moved from a telecom information science program and work at Syracuse University. But I collaborate with a lot of engineers, as that is my main technical background, and mostly in the wireless world. I'm also, by the way, member of the IEEE 1900.5 standardization group, which builds several standards, which I'll talk about today. But you know, disclaimer: my opinions are not the opinions of the work group; they're just mine. Okay. So the outline for the talk is the following. I'll start with some introduction as to why we need better and more efficient mechanisms to do spectrum management, especially as we move towards dynamic spectrum access environments and spectrum sharing. So I'll mention some of the regulatory initiatives that promote spectrum sharing, with a particular emphasis on the citizens' broadband radio service that has been, let's say, regulated recently. And then I'll move on to describing several standards that IEEE has been developing in the area of dynamic spectrum access, with particular emphasis on these two, which are the ones I'm more heavily involved with. And within those, this in particular, which I think you'll find pretty interesting. So for that standard, the standard method for modeling spectrum consumptions, I'll describe what the spectrum consumption model is and how it facilitates spectrum sharing behaviors. And yeah, I think I'll have time to introduce two use cases, a description of a tool that I helped develop for promoting spectrum consumption models, and then I'll end with some perspectives and conclusions. So it shouldn't be too hard to convince this audience that the spectrum is a very important resource for enabling a lot of interesting applications in the mobile world, and we all know that the use of spectrum is the use of mobile data is increasing, which places more and more demands on spectrum as the key resource for mobile communications again. So we all see these graphs over and over and over. There's more use. There's going to be more use of the spectrum. We need to do something about it. So spectrum management. Well, the goal of spectrum management is, like it says there, maximize the gains to society related to the use of radio spectrum. So spectrum as a resource has to be adequately managed. And the issue is that with these new demands on spectrum, we need new mechanisms to manage it, because the previous traditional mechanisms have not kept up with the increasing demands. So we need to modernize spectrum management. Stop having pizza allocations and assignments like those, okay? And in particular because we need to prepare for the growth of mobile data, as I was mentioning in the previous slide. So all of these new enhancements to spectrum management are taking place from a technical standpoint, from a regulatory standpoint, and even from an economic standpoint. So just to kind of make a long story short as to what spectrum management actually covers. In spectrum management scenarios or frameworks, you could be all the way on the license side, where, fully licensed side, where if an entity wants to use spectrum, they have to get a license. So when that happens, you get that entity has a lot of power in terms of managing the quality of service delivered in that band or in those channels, but only very few can obtain those licenses and participate in such environments. Way the other side, you have unlicensed operation, in which you don't have a lot of mechanisms or straightforward mechanisms to handle quality and range and determine who gets to use what. So you have to get very creative to enable some of those things. But it allows entry to the use of spectrum to many other devices and many different entities. So right in the middle of these two types of regimes, spectrum management regimes, you have dynamic spectrum access, in which you can, let's say, tailor how restricted or how well you want to manage your quality of service, and what types of collaborations, behaviors, etc., can you allow to, let's say, share a spectrum as a resource. Okay. So with that in mind, and that's just a brief introduction. Sorry. An interesting thing that has been happening in the U.S. is that, well, in other countries, but I focus in the U.S., is that since the year 2000, the FCC has been releasing policy that tries to modernize spectrum management. And they've been hearing, they've been listening to the academic, let's say, sector, well, also the military sector, in regards as to how to modernize spectrum management. So throughout the years, they gone and produced rules for, let's say, secondary use, spectrum trading, spectrum markets, spectrum leasing. This is a notice of information, so a requirement for information on, what other technologies should we use. But key things started happening around 2010. So in 2010, there was this memorandum saying, so it was the government basically putting out a directive saying, well, the military has a lot of spectrum, but that spectrum is not heavily used. We should make it available for commercial use. So that it was the start of how do we enable that spectrum that has a primary user, an incumbent user in the military, how do we make that spectrum available for commercial use? And there were some goals set as to what spectrum and how much of that spectrum, again from the military, should move into commercial use, and some initial thinking as to how that should take place. So with that directive, in 2012, there was a report that came out from PCAS, is the Presidential Committee, something like Presidential Advisory Committee on Science and Technology, something like that. Okay. And basically, that report laid out the rules and the initiatives for sharing between federal incumbent users of certain bands and the commercial world. So, but the main idea that they introduced is this idea of spectrum sharing, not just being way on the fully licensed side, or being way on the unlicensed side. Again, something in the middle. So the sharing means basically protection from interference without exclusivity. You don't own the license, but you will be protected with interference. So in this case, you're sharing the military band. And they also propose a 3-tier framework to explore flexible use within the sharing mechanism. And that's what ended up becoming the Citizens Broadband Radio Service a few years later. So it all basically started with this. And so, again, taking this as the guideline, and throughout the years, the FCC released some notices of inquiry, notices of inquiry, and notices for proposed rulemaking related to how to implement the vision laid out in this report as to how to basically implement spectrum sharing in the US. And the band selected for that was the 3.5 gigahertz band. Okay. So then finally in 2015, actually the first set of rules for enabling spectrum sharing in the 3.5 gigahertz band came out. So the band actually goes from 3550 to 3700. So some people say, why don't call it the 3.6 gigahertz band, because more the 6, anyway, people just refer to it as 3.5 gigahertz band. So the operation in that band with this sharing framework, which I'll explain in a while, is what's known as Citizens Broadband Radio Service. Now, the rules for operation in that band had been updated in 2016. So again, the first set came in 2015. A revision came out in 2016. And then a proposal for further revisions was released in 2017. And there were many, many discussions, again, around that proposal, especially from comments from industry and entities that were going to provide services in the 3.5 gigahertz band, but they were not, let's say, happy with some of the parameters for operation to provide those services. It's kind of funny to read all the comments that come from groups. You know, some groups want a lot more control on the spectrum, others want more liberty in the spectrum, and then the FCC has to kind of say, well, okay, we're going to do this. So some people are not going to be happy, other people are going to be more happy, and you see like bands that they always want to be very restrictive, and other bands want to be very, very liberal. So I try to be more open, liberal, but anyway. But so the final rules, based on all the comments. So again, so the suggestion for changes was released in 2017, and then it finally was determined last month, what the new rules were going to be. So that's kind of brand new stuff. So this is the band. Okay, so this is where military naval radars have been operating. So that's the band that's being used in CBRS, and where spectrum sharing is going to be tested in the US. And I call it a test because if it works in this band, it's going to be used in several other bands. And there are, the FCC has released notices for proposed rulemaking that request comments in regards to, should we use spectrum sharing in this band? So it's not the only band that is being targeted for spectrum sharing mechanisms. So this is the way they decided to do it in the 3.5 gigahertz band, and it's good to know about it because, again, it might be used in other bands. So there's a three-tier model for the use in this band. Tier 1 are the incumbents, so these guys, military and some satellite stations. And Tier 2 and Tier 3 are the bands that constitute the CBRS service. Okay, so this is CBRS, these two guys. Okay, so Tier 2 is called priority access. So these are users that can operate 10 megahertz channels on this band, but they have to pay a fee. So they're protected by paying that fee. They're protected from interference from the lower the lower Tier 3 guys. I'll mention a little bit more about this in the next slide. So basically, Tier 2 gets protection of interference in exchange for fee. There are up to 10 megahertz channels. One of the changes that took place in the rules released last month is that the term of the license got expanded to 10 years. It used to be 3 years, now it's 10 years. So there was an economical justification for that because we don't want to invest on equipment and so forth if we're only going to have the license for 3 years. That's kind of a summary of their argument. There's a lot more to it, but that's kind of a summary. And then they also, and the area where that license is effective is a county. Before the rules that were released last month, it used to be a census tract, which is very small. Right? They vary in size along the US, but so anywhere from I don't know, 2 square miles up to 40 square miles, but so it's not consistent. But so again, we don't want to have a license on a small piece of geographical area. We want to have the license in a more manageable piece of geographical area, so they changed it to county. A lot of arguments as to why to do that. But that's the rule now.
So I guess, so census tracts I thought were supposed to be roughly the same population.
Yes.
So that would kind of make sense. But counties could be
huge,
you know, like
huge.
Brooklyn's a county.
Yeah, so
that has, you know, 2 million people or something.
Yeah, I'm still trying to wrap my head around the consequences of this, because
I was just curious.
So
then there was a big debate, like what was the?
So you know, to me, it's actually more interesting in the sense that somehow radio waves don't care about counties. Right?
So what?
Yeah.
Radio waves don't necessarily care about counties. I mean, so. Yes. If I'm at the border of the county and I'm interfering with the guys in the other county, who's, you know?
Well, but that same issue was coming up with census tract, where you have but it's
you
more.
do centroid of census tract, and I don't know.
But so if you read the comments, and again, I haven't read all of the way these rules got established because it was just a month ago, and I haven't had time to do due diligence on that. So somebody, I think it was AT&T or somebody, brought a scenario where they say, well, if we wanted to operate, it was somewhere in New York State, we would need, I don't know, like to ask for licenses like in 200 census tract because the population density was high enough to do that, right? But if it was a county, it was just like 1 or 2. And so from an administrative and management perspective, an overhead
They need
perspective.
some way to divide by area, but they didn't want to do something complicated.
Yes, yes. And then the assignment of channels was per census tract, and now it just simplifies a lot of operations. But I don't know, there are other consequences.
Yeah.
Yeah. So, oh, okay. And so tier 3 is general authorized access. So they have no protections against interference. So basically these are opportunistic devices that go into the van, but there are at least 80 megahertz for them to do so.
So let me ask one question for the tier 3.
Yeah.
Can I be a tier 3?
Yes, but you have to register with a spectrum access system, like which is what the next part. So these are the different tiers of operation, but the whole architecture is kind of laid out here. So so the whole coordination of who gets to operate where is via what's known as a spectrum access system. So this is an entity that's basically setting up a database, right? And so devices, CBSD, Citizens Broadband Radio Service Device, just think of them as base stations, because most of the tests have been done with a small LTE base stations. So I'm thinking LTE here. Okay? So these devices have to request a channel. They have to be affiliated with a SaaS. So there are at least around 10 companies that are going to be SaaS operators: Google, Federated Wireless, and some others. I can't remember them all. Okay? So these are companies that are laying out this infrastructure to say, okay, your devices will be able to talk to us, right? So if you're paying us a fee, we register your device. We know that, I don't know, MAC address and some other identifier. So when you turn on that device somewhere in the U.S., he will talk via this channel with our SaaS infrastructure, and we'll register him. And based on where he wants to operate, we'll give him a channel. Okay. And if he's going to be priority access, right? We're going to give him a channel. If he's going to be DAA, we're also going to give him a channel, but he'll be treated different. Okay? But every device has to go through a SaaS. Okay? Every device has to ask the channel through a SaaS. So yes, if you're DAA, you can use the van, but you have to talk to a SaaS.
And the way I talk to SaaS is dependent on which device I'm using, right?
Well,
I mean, am I allowed? Are these devices still certified by FCC or not?
Yes, yes.
That's
and the protocol has already been standardized.
Yeah, that's fine. That's easy.
Yeah.
I'm more worried about the device, right? So I
Yes.
have to certify my device in the FCC.
Yes, and I think also within the last month, maybe Nokia, I can't remember. Somebody certifies it. Oh, the devices are coming, great. And Google and others, they say, we're going to start SaaS operations January. I was at the Wireless Innovation Forum conference, which is the one building the standards for this, by the way, 2 weeks ago. So they were very, very, very optimistic that they'll launch.
Let me try to understand. So the model is manufacturers make devices that have this protocol built in. When you put the base station out there, it contacts this database through, or the SaaS, through some like wired network or something, or whatever, some third network, and then based on your location, it's going to allocate channels.
Yes, and then the functionality of the SaaS is to avoid interference.
Right. So there's some algorithm that, like based on these tiers, that based on your location, that you
exactly. And so the differentiator between SaaSes is going to be how efficient they are in managing, interference and so forth.
It's like when you just turn on, that's it. Like it's not
Sorry?
like, I mean, you don't do this protocol that. I mean, how often do you update or get new channels, whatever? I guess.
So
like
once you get a channel,
how long?
Is there an allocation
when does it
procedure?
expire? Or
yes,
whatever?
so there's allocation procedure and there's a keep alive procedure.
Yeah.
So if you're not using the channel, you lose it because this is sharing. Okay. So,
right, so
how would you determine if I'm using it or not?
There is a requirement for the device to send like a keep alive message to the
Oh,
SaaS.
I'll send a keep alive message.
Something like
No
that.
problem.
I'm calling it keep alive. The standard calls it something else.
Okay.
Yeah.
Sure.
And so there's a requirement for that. There's also
Do I have to report usage?
not direct. Well, yes, indirectly, yes, but
In other words, I just keep it up, you know.
No,
Squatting,
no,
right?
it has to.
Exactly.
It has to be used. It actually has to be used, right?
Oh, come on, it's also easy, you know, it's a
Yeah, so you start faking
so
it.
you start pinging, you just ping
Yeah,
something, right?
so that's some of the stuff I want to look at it more in detail in the root. Well, what if I'm just hoarding spectrum, right? And they want to avoid that. They want to avoid
Doesn't mean
that.
squatting.
Who's gonna, I mean,
Yeah.
you know, if
Yeah.
I'm not paying for it,
Yes.
that's a fundamental problem. If I'm not paying for it, I have all the
No,
incentives
but
to
they have,
hoard
right,
it,
but
right?
the way they set it up is if you're a paid user, then the SaaS wouldn't give you that.
Yeah, forget
Yes.
that. I jump on,
Right,
I'm unpaid, right?
right, right.
Yeah.
I mean, I'm tier 2,
Right, then it's
but I
first
jump
come,
on
first
and
serve
grab it,
squatting.
and
Yeah,
Yeah.
screw
Yeah,
you.
but
Right.
again, if you're not using it, you're supposed to lose it. So even
Yeah,
if
I'll send ping traffic, I'm pinging, you know.
yeah.
No, because if it's free, that's what is gonna
That's
happen.
what happens.
Yes. Yes.
Everything free means, you know.
Yes. But everything, even if you're GIA, you have to ask permission for the SaaS.
Sure, I'll
to give it
ask,
to you.
you know, I'll be the January
Yeah.
1st,
Yeah.
you know, January
Yeah, but-
1st midnight in 2 minutes, I'll ask for it, and that's it, I'm done. Right. I grab everything
Everybody
in New
hammers
Jersey
the
and,
SaaS when it first comes up to try to
Yes.
get the resource.
Yes.
because it's free,
And
right?
also each device has to report. So each device will be acting as a sensor of their spectrum environment to
Sure, and I'll report false.
to help the SaaS make better
Coordinate,
allocations. Yeah. So that's
Is
something
that
to say.
standardized also?
So Yes.
The reporting and how do you measure, is that standardized?
that's a good question. I'm almost certain that it is, but I
Better
haven't,
be,
I
otherwise-
haven't looked at the protocol to do that yet. Okay. It's like 10 documents that Windows Innovation Forum has produced, and I've only read 2 of them, like in a lot of detail. Oh wait, I haven't finished with it. So SaaSes must also, there's also a protocol for SaaSes to communicate with each other. Why am I not using this? And that's also been standardized. So some devices will register with this SaaS, some other devices will register with this SaaS, even in the same geographical area. So they need to share their information so that they won't admit some device that will cause interference to devices that are registered to another device. And then there's this guy called the environmental sensing capability. So this is a database and a set of sensors just to detect federal users or military users, okay, because they're sensitive, right? So this infrastructure, which has been already installed, will say, well, this harbor or there are some ships, military ships that are coming. Please tell your registered devices to move out of their channels, or these channels, because they're going to cause interference to military.
Your channel.
What?
There's a way to revoke your channel.
Yes.
Okay.
Yes.
So see,
Because
that might be a way to.
because
Well, but again, they will revoke you, but then everybody else who tries to get the channel has to constantly try to get the channel, which
Yeah.
is denial of
Yeah,
service,
yeah.
right? I mean,
There-
the more you try, the more
there are protections, some protections. There's a security protocol.
No, that's okay, but I mean, let's say I'm hoarding it.
Yeah.
January 1st,
You're holding
midnight plus
Spectrum.
2 minutes.
Yeah.
I go to Spectrum.
Yeah.
Somebody else wants to get it. They ask for it, they don't get it because I
Yes.
already have it.
Yeah.
Now, if I'm counting, if I'm the one who is trying to get it and didn't get it,
Yeah.
I will keep trying.
Yeah.
And that's, if there are enough of us keep trying, that's by definition denial of service.
Yeah, I see.
And I'm hoping that there will be some revocation and I'll be able to jump in,
Yes.
right?
Yeah.
Ooh, I
So
love this.
I should
This
look
is
at the
research.
rules. Yeah.
We'll be
Yeah.
doing research on
Yeah.
denial of service
Yeah.
Well,
stuff.
we deal with this
Yeah.
problem with the student registrations. Trying to get
Yes,
it.
exactly. Midnight. I mean, that's the same
There's only so
thing.
many
For
slots,
limited number of
seats,
courses,
whatever, yeah.
right? I mean,
Yeah,
they go, they
seats,
start
yeah.
push, submit,
Yes.
submit, right? I mean, it's-
We should look at that.
There's only so many seats. Only so
So-
many channels.
So there are some additional rules, and a bunch of other rules, but there are some additional rules to mention. So priority access licensees and GIAs, they must not, nobody can interfere with the
Big
top guys, okay? And they must accept interference from them, okay? And GIAs, they're lowest level, so must not cause harmful interference to priority access, and they must accept interference from priority access licenses, okay? There are a lot more details.
Are there power limits?
Yes.
Different power limits. I mean,
No. So So for any device, for PALs, for protected access licensees, the protection area, I think that's is the area of -90, where you have -96 dBms over 10 hertz. So no other device can exist within that area. And then if there are other devices operating in the same, well, geographical area, those devices, especially GAA devices, must not cause more than -80 dBms per 10 megahertz to the service area of the PAL.
So if you're on the edge, your chances are you have to reduce your power.
Well, no. Well, yeah, you could do that, but there are two standardized power levels for devices. So there's a.
So no, wait, but that's the maximum power. Can I go lower?
Yes, you can go lower. Yes, you can go lower.
So I can operate potential. So how does SAS determine if I'm causing enough interference or not? It always assumes I'm using max power, right?
No, well, the device should report to the SAS what power it's going to use. So there are two standardized power levels, maximum power levels, but the device could decide to operate at a lower level, but it has to tell the SAS the power.
And you're telling me SAS will use that to figure it? Oh my God.
Yes. So they're all counting that it's going to work well.
Beautiful. Oh, we have 5 years of security research on this. Yeah,
they're hiring people like crazy,
oh.
by the way.
Yeah, no, I know. I'm just, this is beautiful. I love it.
Good. Yeah.
I mean, come on, just think about this.
Yes.
Can you imagine the mess you can make with the wrong algorithm on the SAS?
Yeah, and so that's what's going to differentiate SASs, like how efficient they are.
And how nicely we can attack those SAS.
So wait, the algorithm's not actually specified?
No.
That's the beautiful
No,
thing.
it's just the power levels, the communication protocol between these guys, well, and also with these guys, and that's it.
Oh.
How you want to operate internally, that's all up to you, right?
And they're optimizing, remember?
Now,
That's like a recipe.
Yep.
Beautiful. I mean, this is research. Beautiful.
Just to
I love it.
just to make you
We have to write a proposal tomorrow.
good or angry, within the regulation says, well, how you determine your protection area? Well, use the IHATA model to determine where you're going to get -96 dBms. And they say, well, we were just going to start with the IHATA model. If we later figure out a better model, maybe we'll put it in. But there's a lot of things like we just hand waved. Like, oh, we need. So there has been a lot of criticisms as to what propagation model.
Of course. I mean, that's a.
Yeah. But so, what are the power? You mentioned there's power. The two power.
There are two power limits.
Yeah. So one is for the protection area, so the area where no other device can live, right, around you. And then there's the aggregate interference limit, and it's aggregate interference.
So what are those?
Which you can't define. I mean, how do you define aggregate interference? I mean,
but no, what are those power levels? Like, did they define in the standard?
Yeah. Well, yeah, the regulation -6 dBms for the over 10 megahertz for the protection area, -80 dBms for the aggregate interference.
But I mean, how do you? This is ridiculous. It's property of the receiver, not property of the transmitter, the interference level. How do you measure that?
So
there you have to have a sensor somewhere.
Yes, and that was actually one kind of part of my conclusion. Well, all of this nice spectrum sharing brings a bunch of issues in terms of we need to monitor the use of spectrum and see if people are complying with the policies and regulations. So we're going to need spectrum sensor networks. Right?
Yeah, but I mean the density of that network is ridiculous.
Well, no, really, I've done some work on that, and there's a point where the degree of additional accuracy that you get for putting more sensors starts.
No, I understand, but even for I mean, just think about, say, New York City, and you deploy something like this, it's a disaster.
Yeah.
I mean, you can't.
But you could crowdsource the sensing, right?
Well,
you could.
Each one of these is a sensor.
No, but then you have to certify every single sensor, because if I start falsely reporting,
but each one of these is going to be a sensor, remember?
No, I understand, but those are few and far between, right? I mean, the ones you want to crowdsource is the ones on the user side.
But normally, I mean, the trust level in the chipsets is pretty high, so.
Yeah, no, it's not.
Mandated that.
No, but you're forgetting one thing. That this is, if I'm AT&T and you're Verizon, I'm going to start screwing you up, okay? Just because I can.
Well,
I'll start reporting wrong.
I
mean, it's the same thing. It's the same thing when they try to do the FCC tried to do the broadband speed tests.
Okay.
Right?
Yeah.
So Verizon immediately said, oh, no problem, I'll locate my test server next to the FCC, right? And therefore report really much better speeds. Right?
Yeah.
Oh.
So there's going to be a lot of issues. Well,
Okay, so but if the SAS is run by some other, like.
Yeah, but if your sensing information comes from user devices,
Yeah.
which is where you really have a true cloud.
But they have to be
outsourcing.
certified by FCC, those devices. Right?
Yeah.
No, right, I mean, it's interesting, the economic incentives between the SAS and the user and the
Exactly.
people
Yeah.
creating
Exactly.
spectrum, so.
Exactly. So that's a
Who
beautiful.
pays for the sensors?
Yeah, yeah.
A lot of
What?
interesting questions there. So yeah, I could go all day talking about.
Yeah, no, absolutely.
So let me shift wheels here and start talking about the standards, and then we'll kind of put both things together. So IEEE standards for dynamic spectrum access and sharing. So these standards are being developed in the IEEE DySPAN Standardization Committee. That DySPAN stands for that, okay? The Dynamic Spectrum Access Network Standards Committee. So the scope is, again, I just mentioned, standards that allow and enable dynamic spectrum access interactions. So these are being developed under the 1900.x series. And as I said, I'm part of one of the work groups. So I mentioned the work groups that have produced standards and that are active, have been recently active. So 1900.1 has produced standards basically on terminology. So just terminology that will be applicable, standardizing terms that will be applicable for dynamic spectrum access and spectrum sharing. Okay, so the first standard was published in 2008, and it has received some updates, and we're actually voting on the last update. I just got the email this morning actually to do the last round of voting. We've been working on it this whole year. 1902 has a long name, for adjacent band interference. Developed in 2008, one of the more popular standards in the series, has been used by many companies, and we're also starting the process of updating it. Every standard that's more than 10 years old needs, by force, to have an update.
When they say coexistence, is this heterogeneous system coexistence or same system?
No, heterogeneous. Yeah, so it covers all that. Yeah. So let me jump to .6. I'll go back to .5 because I'm going to spend a lot of time on .5, but let me go back to .6. So .6 is standardizing spectrum sensors. Okay, but basically how spectrum sensors communicate with each other, how they're going to report data, and how they're going to talk with artifacts like databases. Okay, so the requirements for this standard were published in 2011, and then amendments. This is typical in IEEE standard. You have one standard that kind of lays out the main architecture, the main requirements, and then you start building amendment standards to deal with the details of each one of the requirements. So .A define the protocols for sensors to talk to each other, and .B standardizes spectrum database interfaces, how to talk with databases. So that's for sensing. Kind of involved in that standard, but not heavily because .5 has taken most of my time. Again, by the way, I'm secretary of this work group, and my opinions are just mine. Not the ones from the work group. Okay. So
don't worry, don't blame you.
Okay. So .5, long name, policy language and architectures for managing cognitive radio for dynamic spectrum access applications. So that's the work group, and then it produced a standard in 2011, which kind of, well, the name says, the idea here is to develop a policy language for devices to be able to communicate the use of spectrum and being managed by policies. So yes, you can do this. No, you can do the so control behaviors of radio systems. I'll go a little bit deeper in a while. So this standard laid out the architecture for how this collaboration and this interaction between devices that are policy driven will take place, and also define the requirements for the language. So in .5.1, that standard focuses just on delivering the language, producing that language. Okay, And it has to be a machine interpretable language that understands what radios are, how they can operate. Again, I'll briefly give some details. 5.2, which is the standard I've been most involved with, as I'm working on both, but this is the one that I spend most of my time. Standard method for modeling spectrum consumption. I'll explain this in a lot more detail. And so it was completed in 2017 and released in 2018, just recently. And we're adding some more information-centric aspects to it. So most of my research deals with information-centric methods for managing spectrum, since I'm in information school. And so that's why I got involved with all of these things. So starting with .5, it defines an architecture, so a policy-based control architecture for controlling the operations of radio systems. Okay? And the focus, like it says here, is the use of machine interpretable policies for managing spectrum. So how do you build a language that can be understood by machines? So if a radio receives a policy in this language, it will tell the radio what behaviors are allowed or not allowed in a given, say, spectrum band or location. Okay. So I won't go into details. Once I did a whole day tutorial on these standards. But this architecture has been referenced by DoD in several requirements, equipment requirements, and a bunch of things. So there's a lot of traction, some traction at least there for this type of architecture. However, we've received several feedback from many different entities, and we need to update the architecture. So we're going to start the work for updating the architecture, make it more modern, make it more consistent with what has happened in the spectrum management world. Well, we're hoping to launch that work early next year. Okay, we're just setting up for it. So, but this is currently the architecture. But within that standard came also the requirements for the policy language, and those are being worked in .5.1. So, the status here is that we started with those requirements from .5. We also had some input from commercial operators, mainly from the Wireless Innovation Forum, as to other things that the language should cover. And so, since 2011, after the first standard was released, some work started on this language. And we're hoping to have it completed in 2019. Progress on this standard has been very slow because it's a big, complex thing. Building something that's machine interpretable that can convey, that understands what a radio is, that understands radio operations, and so forth.
So how does it relate to similar attempts on the management for the devices themselves, the operation of the devices? So forget about policy. There is like a bunch of attempts to create these software-defined networking-based configuration tools and stuff.
Yes.
So how does that interface with this? Which is eventually they have to.
Yes. So that's a very interesting point. So one of the updates that we want to put on the architecture is that it should cover not just devices but networks.
Sure.
Right. So it's radio networks, not just devices. So one of the kind of, let's say, weaknesses is that there was a very device-centric approach, but now we want to make it more network-based. So we're going there, but we still haven't figured out quite well where to do that. Something I want to contribute in because I do stuff on network virtualization as the end.
That's at some level it's a little bit dangerous because if you just concentrate on devices first, I would agree you need something on networks, but you might want to think about some kind of layering because just the devices is much easier to reason about, and then and the networking or something.
That's where the other standard I'm going to talk about helps.
Okay.
Good, but good. So when we started work, when the work group started work on this in 2011, they saw that this work was going to be a monster. Okay, and so just to make a long story short, part of the approach to developing the language is to reuse several standards, from the semantic web world. So they're called RDF, Resource Description Framework. Basically, these are standards that allow you to configure, actually create language primitives for how to share information, between machines and so forth, how to build a vocabulary, how to make a vocabulary that's consistent with an ontology language. So an ontology describes a set of knowledge. So we have let's call it the cognitive radio ontology, that basically is a description of what's a cognitive radio, what's a radio device, what's a band, what's a transmitter, what's a filter, what's a frequency, all of this. So all of this has to be integrated in such a way that the language can manipulate an ontology that in this case describes radio operations, that can describe rules for behavior. So there's a rule language, also comes as part of the semantic web standards. So basically we're trying to integrate RDF with ontology, with a rule language. I can't remember the name right now, and have language primitives that operate under one type of logic, right? And can allow, can be used to define policies that permit a behavior, prohibit a behavior, specify a behavior is optional, and so forth. So basically, the language at the end should allow for reasoning in a DSA context. So I could have a policy that says a device can operate in this band, let's say 4 gigahertz band or 6 gigahertz band. Let's say a device can operate in this band as long as there's not a higher priority user or incumbent user. Okay. So then questions come as to, well, how does the device detect that there's an incumbent user? Does it use energy detection? Does it use some other mechanism? Because the policy is just saying, yes, just make sure there's not a priority user in the band, and then if there isn't, you go for it. Right? But how does it make its decision? That's not part of the language. So there are some extensions for calling sensors, for calling stuff. But when we started questioning, what happens in this scenario? What happens in this scenario? We were seeing, oh, we still need to add some other stuff on the language. So basically, what started happening is that this very top-down approach was getting, it's really big, it's a really monster. And so while we had a group working on that, there was another initiative to start more from a bottom-up approach, okay? And asking ourselves, well, what's the most important thing that, if standardized, could alleviate a lot of the pressures on the language and a dynamic spectrum access system? So this is where spectrum consumption models come in. Okay, so work on this started in 2012 as I joined the work group, and as a guy from MITRE joined the group, John Stein, who had been working on this concept for a couple of years and brought it up to our standardization group. So we joined the group at the same time. We also found out that we had the same mentor at the University of Texas at Austin, but we didn't meet in Texas. We just met at the start of this group in 2012. So the key thing is that dynamic sharing spectrum requires the definition of the boundaries of spectrum use. Okay, but what are those boundaries? So basically, we need something to be able to specify how a transmitter emits radiation, from a receiver's perspective, what's interference to the receiver, what's a listen before talk policy, how could you express that in a machine interpretable way, but being very consistent. And the idea is we had this directive, so a common means to define spectrum use would enhance spectrum sharing. So basically we create an information model that captures the main characteristics of how a device uses spectrum. Exchanging those models would allow for many different dynamic behaviors in spectrum use across many entities. So that was like the key driver, right? So we aim to have spectrum consumption models capture the minimal amount of data for spectrum management purposes. Okay, so with that perspective in mind, we treat SCMs, the design of SCMs, and this again part of the work from John Stein, treat SCMs as a loose coupler. So loose coupler is a concept from mechanical design theory, mechanical engineering theory, where it's a minimal interface or a minimal model that allows innovation on the application side, on the infrastructure side. So an example of a loose coupler is the IP protocol, right? So on the IP protocol, you can have any application, any network application, as long as that network application can somehow, through a transport layer or whatever, deliver its information in IP packets. Then those IP packets can be carried anywhere. Okay, so application can be developed however, as everybody just standardizes to IP. And on the infrastructure side, you can build networks however you want, radio, fiber, whatever, but as long as they can have the capability of carrying IP packets, then they can deliver information from many different types of applications. Another example of a loose coupler is the power outlet, right? So on the infrastructure side, so we just want 120 volts, 60 hertz on that thing. We don't care how it gets there, okay? So it could be wind, geothermal, nuclear, whatever. As long as the infrastructure delivers that, we're good. And then on the application side, you can just plug whatever you want in there, as long as whatever you plug can accept power in 120, 60 hertz. Right? So you can plug a toaster, a microwave oven, a panini maker, and I think I'm hungry. Okay, but sorry. Yeah. So, but you get the point. So the idea is that with SCMs, you would allow for any type of network operations or spectrum management system to have their own algorithms to manage spectrum and so forth. But once it makes a decision as to what spectrum should be used by a device and so forth, it will convey that to be an SCM. On the lower side, SCMs, if devices exchange SCMs with them by whatever infrastructure, it would allow for innovation on dynamic spectrum access behaviors. Okay, so that's the idea. So, but along with the models, with this information model, comes a set of means to compute compatibility between any two models. So the rules that say, well, if you have two models, to validate if the operation of those radios as expressed in those two models is going to be compatible, by which we mean non-interfering, you have to use these rules. Okay, those have been well defined. So you use this value from this construct in the model, and use this equation, and do this and do this, and everybody's going to, the result's going to tell you the two models are going to be compatible. And those rules are also standardized, so nobody can fight, which happens nowadays, that, oh, but I use this propagation model, I use this rule data, this terrain database, and so forth, and everybody gets two different results. The point here is to avoid all of that. Just have one standard information model, one standard set of rules to evaluate compatibility. So, then, with that introduction, this is what the standard accomplishes. So these are the objectives of the standard. Defines a data model for what goes into an SCM, how to arbitrate compatibility, and how to generate SCMs that are machine readable. And so I was saying before, the standard was released just recently. Okay. So these are the constructs. Let me just take a sip here. So there are 11 constructs. Some of them are required, others are optional, especially these top are required. So, and remember, the idea is to capture the minimal amount of information for conveying the consumption of spectrum by a transmitter or receiver device, because a receiver device is also consuming spectrum. So reference power, spectrum mass, constructs to capture the spectral content and signal characteristics. Underlay mask, that's for characterizing the filter and the receiver. Power map, the direction, how the antenna radiates power. Propagation map, capture environmental effects. Then you have these to handle intermodulation aspect. This location and schedule, right, to enable higher resolution, as it says there. Minimum power spectral flux densities, construct we have to add to address broadcasters, like TV broadcaster behavior, has some history. And protocol or policy to specify behaviors that enable compatible reuse, like you're going to be using a listen before talk policy, and so we can put that in that construct, okay? And so those are the main constructs, and one thing to mention is that most constructs have a probability element, So it's not like, oh, this is the value. I mean, I'm like 100% confident that this is how my device operates. You can tailor the information in the construct to say, well, with 80% confidence, I'm operating like this. With 90% confidence, I'm operating like this, and so forth. So that helps with the compatibility computations in some cases where there's not a precise value. Okay. So so basically, with that information, you can build a description of a transmitter. So we call those transmitter models. You can build a description of a receiver. We call that a receiver model. Then you can combine transmitter receiver models into a system model, and combinations of system and other models into set models. So as an example, a system model could be a description of all the Verizon base stations in the New Brunswick area. Okay, so that would be a system model, and the idea is that the header of that model would collect the aggregate use of spectrum for those base stations. So when you're doing a compatibility computation, if you're compatible with the aggregate, you don't need to do a compatibility with each one of the transmitters. So if you're compatible with the aggregate, you are. But if you're not compatible with that header, with that aggregate, then you might need to go in and see, okay, which was the transmitter or receiver that made this not compatible. And then maybe my new base station is not going to be able to operate in some neighborhood because that's where the base station from Verizon would cause interference. Okay? But with this type of aggregation, the other thing that's worth mentioning is that you can build what are known as spectrum authorization sets and spectrum constraint sets. So that would be a description that, for the case of authorization set, that says these are the boundaries where you can actually use spectrum in the same given area. And with spectrum constraint set, it's a list of system and receiver models identifying existing users, saying, okay, these places in the spectrum have already been used or already have used it. You cannot go into them. Okay, so there's a lot of flexibility to convey some very basic policies, like this is allowed, this is not allowed type policies with just SCMs. Okay, so just to go a little bit more in detail. By the way, how much time do I have? How long?
No, you can go.
Okay.
I just have to step out for.
Okay, sorry. So
you can continue.
So with these constructs, basically. On the transmitter side, you use the reference power plus the spectrum mask, right, and the antenna radiation pattern information to compute a power spectral flux density of transmission at the antenna. So, and then you use the propagation map to say, well, the energy of the antenna is going to be actuating this way or to a given distance. By the way, this is a log normal propagation map. Everything has to be reduced to that type of propagation map because the idea is not to have any dependencies on external information resources. Okay, and then on the receiver, you're using these. You're using your underlay mask, and your antenna receive pattern to compute the allowed power spectral flux density of interference. And then if your energy is not going to violate that threshold, then they're compatible. If not, then there's going to be interference. So there's no magic stuff happening here. It's just a basic link budget computation. Okay. So all that the model, all that information in the model provides us for these basic link budget computations, which for the case of two devices, they're very easy to compute. But when you start having a lot, so it's getting really tricky. And again, the other main benefit is to have this standardized so that it doesn't depend on external information sources. Okay, so the general process of computing compatibility is, well, okay, you have say two devices. You first determine if the uses will operate in time and spectrum. So two devices trying to use spectrum at the same time and same location.
So sorry, where are the policy rules encoded? Like
well,
certain transmitters have to have priority. Like those kind of policies.
We're not covering that in the model.
Okay.
We're just saying how they consume spectrum. The priority behaviors could be encoded in the language,
Okay.
So basically, where we're going is that SCMs are going to be a primitive of the policy language. Okay, but then the policy language is the one that's going to allow handling priorities and all of that. That's not directly included here. Okay.
So this is just
yeah, an information model. Right? So so the terminated uses, but having said that, SCMs could still be used to define very basic policies, like this is allowed, this is not allowed. Right? But if you want very complex policies, like I'm a level 3, is there a level? I go before level 4 and level 5. Can I transmit that? Those would be covered in the language. Yeah. So if there are two simultaneous users in a given geographical space and channel, then you go to the next step. Determine the constraining points of operation. So where are the directions of emission of power from the transmitter or receiver that are going to be the worst, okay? That are going to either potentially cause the greatest interference to this guy, or from this guy, the highest potential interference to this other guy. So those are what we call constraining points. Then once you found those, compute the allowed transmit power at that. So are we going to not be compatible? Is the energy from this guy, sorry, in this case is the secondary affecting this guy, is the energy from this guy going to affect this guy, okay? So like it says there, determining those constraining points, that's the key difficulty in dealing with this computation. So for two devices, that's not hard to do. But when you start having a lot of them, it becomes computationally intensive, okay? So I'll describe some issues related to that in a few slides. But basically, with SCMs, we can move towards something that we could call model-based spectrum management. So it's spectrum management based on the use of spectrum contortion models. And remember that SCMs just captured the basics of each device. So if there are any proprietary things happening on the device, those can be hidden from the model. So some people like that, especially in the military. They like that they don't have to reveal some stuff. Okay, and the rules to evaluate the computation are standardized. So whoever evaluates the compatibility with those rules will get the same result. Okay, so with the models, basically. From a technology perspective, SCMs can convey spectrum, could be used to tell a device how to operate. So you could use, you could have a radio, and actually it's one of the things, it's one of the experiments I want to do next semester. You tell a radio how to configure itself just by reading an SCM, okay? And making sure that the SCM that it employs is compatible with all the other operations of other radios on its neighborhood. So you can tell radios how to behave via an SCM. From a commerce perspective, you can use SCMs to enhance spectrum trading, spectrum leasing interactions. From a regulatory perspective, it could be used to define spectrum usage rights. Okay, so that's where we're going to take this. So let me just show you two use cases for SCMs. So SCMs could be used in a spectrum access system implementations, where in particular for the interface between the SASs, one SAS could give out, like say, a summarized view of the devices that have registered and that are operating under this SAS. So it could give a summarized view of how spectrum is being used by the devices registered to the SAS via an SCM, right? So this communication interface could be implemented in SCMs. For the current regulations that are out there for CBSD, we actually talked with the guys building the standards. They did not take the standard into the regulations. There were some competing interests. I won't get into that. But the point is that since spectrum sharing and a SAS-based mechanism for spectrum sharing is also being considered in other bands, those implementations could potentially, if the guys moving those implementations agree to, could potentially use SCMs. Okay. and as I mentioned, you could also tell a radio device how to operate via SAS. So you could have some potential use for access on this interface also. ESC vendors could standardize on SCMs to say, well, what channels should be vacated in a particular area when a military user gets detected by the ESC, and CBSD devices need to then vacate a given region. So there are some interesting perspectives as to where SAS SCMs could be used. Oh, by the way, did I mention that? Yeah, so some of this work has been done in cooperation with MITRE, so that's why you see the MITRE logo in some of the slides. And we were presenting some of these slides 2 weeks ago. So one of the specific projects that MITRE has been working on, this came from my collaborator, is how to do very dynamic and quick spectrum deconfliction in certain scenarios. They have DoD as a customer, so I won't get into that. Yeah. So if you have several, let's say, trucks or convoys moving, and they're all using wireless communication in a given area, how you quickly deconflict and build a spectrum assignment decision for all of them as they're moving, right? So then this was the scenario with no deconfliction, this is the scenario with deconfliction, and unfortunately the slides didn't capture the video, but we had a video that showed, well, as they're moving through this area, they're using the information in SCMs and some a framework that uses the compatibility computations defined in the standard to quickly deconflict and make spectrum assignments as they're moving. Okay, so the focus in MITRE is to build these algorithms so that they run really, really fast and are really scalable. Okay, so that's basically what they're working on. So those are just two scenarios. And now, if you wanted to work with SCMs, actually, in a couple years ago, 3 years ago or so, I got a grant from Google to build an open source tool that would promote use of the standard. And Google is SAS operator, by the way, Spectrum Access System operator. So we called it the SCM BAT tool, the Spectrum Consumption Model Builder and Analysis tool, and it's here in GitHub. Okay? So this tool basically offers a GUI for the creation of SCMs and formatting that SCM into an actual SCM document, which is, in this case, is an XML document. I'll say more about that in a while. And the tool also offers a set of capabilities for you to import SCMs and generate a compatibility computation against them. So these are just some screenshots. So you can start creating a new consumption model, open a new one, and execute a compatibility test. Here are the tabs to start creating a model, a transmission model. Some of this has changed. We're updating the code with some students, but haven't done much this semester. So if you we're defining one of the constructs, which is spectrum mask, right? So you have this kind of layout, and so if you wanted to create this spectrum mask, you would input the inflection points for the spectrum mask. Unfortunately, we don't have the capability to generate this graph as the spectrum mask is being defined. This comes from MATLAB. It's not a capability that's inside the tool, but we need to add it. So it's one of the enhancements that we're thinking of. But yeah, there are others. So when you execute a compatibility computation, this is an example where you have several narrowband transmitters against a receiver. And so it will tell you, well, these transmitters will interfere with the receiver if they operate at the same time. If these two operate alone, they won't interfere, and so forth. So it does a one-to-many a combinatorial analysis as to which guys can be operating at a given moment in time, which guys cannot, who's going to be compatible, who's not going to be compatible. So it goes through that and generates a report saying, well, what behaviors will allow compatibility, non-interfering behavior, and which what behaviors won't. And actually that's laid out as an HTML page. This is not updated. So now it's just an HTML report which you could publish on a website or send to somebody else. Okay. So I just need 2 more slides and I'll finish. So for some future perspectives on spectrum management, spectrum sharing is becoming more and more common, so understanding how spectrum sharing is being regulated, the architecture. So I talked about the Citizens Broadband Radio Service architecture. That kind of architecture is kind of being mentioned in a lot of the new regulations that or requests for information for regulations that are coming out of the FCC. Other countries are looking at what the U.S. is doing in this space and may adopt the very same rules. In Europe, there are some similar rules, but they're not exactly the same. License share access, I don't know if you've heard about it, LSA. So other things that are coming is in the current regulations for CBRS and then the new prospective regulations for sharing in other bands, they always mention secondary markets and behaviors, and that the regulators are going to allow behaviors where if you have a 10 megahertz channel but you're not using all of that channel, you can lease that part that you're not using, or you can submit that part to for use and a request in a secondary market. So that's allowed, which kind of makes the sharing coordination a little bit trickier. But overall, with all these new spectrum sharing coming into play, an issue I see as worrisome is monitoring and enforcement of PSA behavior. So yes, it's nice that regulators are allowing all of this, but how do you make sure that everybody is behaving correctly? Okay, so that potentially calls for the use of spectrum sensor networks. How you build capabilities to enforce and monitor spectrum policies, especially when you're allowing spectrum sharing. So that's a key question that I'm interested in exploring. I've done some work on spectrum sensing. So some conclusions then. So SCMs are basically a standard that we hope will help support many spectrum sharing and dynamic spectrum access capabilities in the future. Especially since innovations like that, by having a common information model, we hope that will incentivize new innovations that allow more spectrum sharing. Work Group 1905 of the IEEE has been working on these standards, which I just talked about. We're actually doing hoping to release the policy language for comment in 2019. We're hoping to release updates to the spectrum consumption model standard so that the information model can be expressed as an XML-based document or an JSON document, because the idea is that these models have to be machine readable, right? So those are standards that we're working on. Next week we're actually meeting in DC to make progress on this. And well, there's more work to do. There's a lot of very nice innovative things that are happening because of spectrum sharing. So hopefully we can collaborate on those. I'll be here working in the lab during my sabbatical next semester, so I'll be glad to talk with any of you to discuss policy, spectrum policy, not world policy, spectrum policy, or technical implementations of TSA. And with that, I'll finish. Thank you.